Some of them are. Hi. Okay, everybody. Today I'm going to tell you how not to prove the Riemann hypothesis. But yeah, but here's the best way. Okay, so I personally like to fantasize about things. I like to sit there and be like, I have like one tiny idea. And then I'm like, well, if this works, then I can prove the Riemann hypothesis. And I'm like, then I'm going to get $1 million and I'm going to get tenure and I'll have self-worth in life and everyone will love me. And it's great. But like, for me to be able to fantasize, I need at least some approach to this that feels a little bit plausible, plausible deniability. What I'm going to give you is that I'm going to give you the ability to fantasize about you yourself, the symplectic geometers of the world, proving the Riemann hypothesis. Woo! Okay, now I think that I didn't actually know anything about the Riemann hypothesis before, or why we really cared. And even though like I feel like I ought to as a person who consumes and exists in math, it's like a classic pop math thing. But like I think what it would be like it would be cool to give like at least one layer deeper, So a lot of this is going to be some like fairly basic analytic number theory about like what we know about the Riemann hypothesis. So for the first part of the talk, I'm basically going to go through Riemann's 1859 paper, which is his only paper on number theory, where he introduced all of this stuff. And I'm going to talk about it. Okay. So let's get started by sort of part 0. The Riemann hypothesis. Let's get started by getting acquainted with our person of interest, the Riemann zeta function. It's going to be defined as follows. The zeta function, I'm going to be drawing a lot of these guys, and sometimes I'll get carried away and write it C. If I do that, you have to yell at me. Okay. The zeta function is going to take as an input a complex number, and it's going to output the sum over all natural numbers. This is not including 0 for the rest of the talk, of 1 divided by n to the power of s. So, for example, zeta of 2 is going to be the sum of the squares, reciprocal squares, which, as we know from Euler, is pi squared over 6. Zeta of 1 is going to be the sum of 1 over n, which diverges, and so on and so forth. Now, a priori, this guy is kind of annoying to work with because zeta of s only converges when the real part of s is greater than or equal to is greater than 1. So as a function, it's not very exciting, but then what we can do is we can analytically continue it. So where this series is defined, it defines an analytic function, which is this guy, analytically continue it to the whole plane. So this is where a lot of people, when they like do their little pop math stuff and they talk about the Riemann zeta function, they spend a lot of time talking about analytically continuation and how cool it is, but you already know that it's cool, so I don't need to convince you of that. But let me give you some facts about this guy. First off, the most basic fact about it, the thing that actually lets us figure out this analytic continuation, is that the Riemann zeta function satisfies a functional equation, which tells us that we can relate the zeta function at some values of s to its value at different values of s. Now, I'm going to copy this down, but the form of this will not matter at all for the talk, but I'm writing it just so you can feel like I'm not lying. Over pi of the sine of pi s over 2 times the gamma function of 1 minus s. The gamma function is the thing that looks like the factorial, the analytic continuation of that. And this is the thing that we understand a lot better than the zeta function. So if we can say something about the zeta function using the gamma function, that makes us happy.
So doesn't 2 pi to the negative s when you're doing complex numbers? Don't you have to like take a branch?
Yeah. So like, how do I do to the things to the negative to the imaginary power? 2 pi to the negative s is going to be e to the negative s log 2 pi, and you have to choose a branch of log and stuff like that.
Because 2 pi is a real number, you can just canonically choose the base.
I mean, it's yeah. I think this is fine.
Okay.
Okay. Now, what I want to point your attention to is this fact. We are relating the value at s to the value at 1 minus s. So let me draw sort of the most important picture, which is that of the complex plane. See here, and I'm going to take off some values here. So we have this value 1, 2, 3, and so on. Now, when I say the value of s is related to the value of 1 minus s, let me represent that for you geometrically. I have this vertical line at the real part of s is equal to 1/2. The functional equation is a reflection around this line. So it lets us take the part where it converges over here, and turns it to the part over here on this side. Now, it converges everywhere beyond this point, which means that after flipping, we understand everything beyond this point.
Does it converge to 0?
Hmm?
Does it converge to 0?
Yeah, I think you might have to do.
Oh, because sine of 0 is 0, and converges back. Well, that converges to 0 at the same rate that harmonic series diverges to infinity.
Yeah.
And so it's either 0 or a finite number, but
it's like 1/2. I think that's the zeta function regularization. I don't know. But yeah, we do get a finite number. Basically, the way that we analytically continue this is by abusing this functional equation. I'm not sure what the answer we get is, but yeah. Now, let me tell you about the zeros and poles of this guy. So we have a pole here at 1, which is this divergent series that we computed up here. That's a pole of the function. And on the other side, we have zeros at -2n for n for in a natural number. So at negative even integers, we have zeros of these functions. These are called the trivial zeros. And this space right here is going to be called the critical strip.
And is it obvious that there are no other zeros outside of the critical strip?
It's obvious in the sense that by messing around with this functional equation, you can get it pretty readily. Riemann does it in his original paper. I don't know how to do it, but I think it's not hard.
So it's not just because zeta on real part greater than 1 should always be non-zero.
I think so.
And then, so all you have to do is understand the gamma function and make sure that if the sign doesn't. Bullshit. Okay.
What's the degree of this pole? Or the order of this pole?
Order 1.
Order 1. Okay, that makes sense.
So the statement is that all other zeros lie in critical strip. That is, the 0 is less than or equal to the real part of the 0 of 1. So the zeros look like this. I don't have enough colors.
And we're including the bounds of this critical strip. Okay.
Maybe not. Doesn't really matter. So I'm kind of bereft of colors. Maybe I'll use white. The zeros look kind of like this. They're either on this line or they're mirrored across this line. That's what we know about it. So this is called the critical line. Okay, and now with all of this in place, we have the statement of the Riemann hypothesis, which is that all zeros of zeta which lie, let's call all zeros rho of zeta, which lie such that their real part is between 0 and 1, so they lie inside the critical strip, have the real part equal to 1. They lie on the critical line. That is the content of the Riemann hypothesis. This is the $1 million question.
Elliot, if you get the $1 million, will you buy me a little coffee?
I'll buy you a little coffee. I'll get pizza every
We can have a pizza party?
Yeah.
We can remember.
Do you know what? Actually, here's a story. In 8th grade, my math teacher went on Wheel of Fortune and won the $1 million prize for the
What?
third time in history. And we all got a Subway party, all of her students.
Wait, what's it like? The sandwich place?
The sandwich place, yeah.
She's gonna get on you guys a little.
I don't know. Yeah, I'm not ashamed.
They continue teaching.
Yeah. I like teaching. It was for a kids' college fund. Okay.
That's really sweet.
Now let me say for you, okay, this is the Riemann hypothesis. Now before I move on, I just want to say one more fact about this, like this function right here, which is my favorite fact about the Riemann zeta function. This does not factor into the rest of the talk at all, but I can't resist saying it. So let's move over here.
Okay, I'm doing the old speech. That thing.
So here is a theorem. I'm going to try to copy down correctly. So let U be a simply connected open set that lies in this region right here between 1/2 and 1 with the real part. So U is contained in the set of things to the right of the critical line, but still inside of the critical strip. Okay. Now, for such sets, what I'm going to say is I'm going to say how every function appears inside the Riemann zeta function. Let me stress this a little bit more. Like what the Riemann hypothesis is saying is that there are no zeros that lie inside of this little region here. So maybe something that maybe it's not really evidence, but something that morally should be true is that, you know, like this function in this region should be positive everywhere. Well, what I'm going to say is that it's positive in the sense that it contains every single other positive harmonic holomorphic function. So what do I mean?
What do you mean by positive?
Not positive, non-zero. Non-zero is what I meant to say. So I'm going to have F from U to C, a holomorphic function, F non-vanishing. So there's no zeros. So here's my little set U. Then the statement is that for all bounds epsilon, I can approximate F by scrolling up and down inside of the Riemann strip, more precisely, inside of the Riemann zeta function. So for all epsilon, there is some time or some t such that the maximal difference inside of U between F of Z and the zeta function applied to Z plus IT is less than epsilon.
That's actually cuckoo bananas.
It's cuckoo
Does
bananas.
this apply to any other? Does this apply to like the other like L functions?
This applies for all L functions, pretty much. L functions are generalizations of zeta-like functions where you plug in different series instead of n into that guy.
But like,
This kind of thing.
huh?
This is generic
What do you mean by generic?
among all holomorphic functions. So, okay, what am I saying here? Let me say this again. Imagine you had a website where on the website you printed out like the value of the zeta function, and you could scroll up and down on this website, like scroll up and down through the critical strip. And this website is special because it acts kind of like a library of Babel. For any non-vanishing holomorphic function on any open set inside of this region, you can scroll long enough to get an arbitrarily close approximation in the L infinity norm of the zeta function with your original function. It's universal. Now, Birkhoff proved that, you know, if I just take a generic, like this is kind of not really special about the zeta function. Like if I take a generic holomorphic function, then I can like translate U in some place to find any given function. Except the only explicit functions we know that have this property are zeta functions and L functions. So it's one of these things where like every if you chose a random one, it would have this property, but most things we know how to write down don't, because polynomials don't do this, you know. Anyway, I think that's really goofy. It's so
I'm
goofy.
obsessed with generic things where there are two examples. Number theory is so cool. Generic numbers are not algebraic, but writing down the non-algebraic numbers is really hard.
Okay.
Wait, can you still see?
Yeah, I'm going over here
Okay,
because.
I see.
Okay, that was a little aside about my favorite fact about the Riemann zeta function. Okay, now here is the content of today's talk, which is what's called the Hilbert-Ploya conjecture.
Wait, you're not going to tell us how to use this for the prime number here?
I'm getting there.
Oh, okay, sorry about that.
So this is motivation for what I'm doing next. I mean, I promised you a way to prove the Riemann hypothesis. Here's an approach.
Who's Ploya?
Ploy is a number theorist.
Oh.
I don't know what he does.
It's Hilbert.
So-
Hilbert.
The story of this goes like this. Ploya was, hanging out with his friend Lev Landau, and Landau asked, "Hey, Ploya, is there some physical interpretation of the Riemann hypothesis? Can I understand this with physics?" And Ploya said, well, I mean, I don't know. I guess if you just found an operator whose eigenvalues were the zeros of the zeta function.
Wait, is it Ploya or Polia? Like as in Polia counting?
Probably the other one.
Oh, Polya is how to solve it.
Okay.
So the goal is, step one, find an operator on some Hilbert space
It is Polya.
such that the eigenvalues of the new operator, which is 1/2 plus I times my first operator, I'm just rotating it so that the spectrum kind of lives on this critical line, are the zeros of zeta. Okay, wishful thinking. Like this is finding such an operator. Okay, suppose we found this. This is like a way of linearizing the problem, constructing the zeros as a spectrum of some operator. 2, show that H hat is self-adjoint.
Is this your procedure how to prove the Riemann hypothesis?
Huh?
Is this how to prove
This is how you prove it, yeah.
What's the conjecture?
So the conjecture is that I can find such an operator and that this is true. I mean, or I guess I could also call this the approach.
This has a problem of your operator needs to not include the trivial zeros. Has to know about them.
This looks bad. Yeah. So, find an operator whose eigenvalues are the zeros of the zeta function. And if you found this operator and the operator is self-adjoint, then the eigenvalues are real QED. If the eigenvalues of this are real, then the eigenvalues of this whole thing lie on the critical strip and you're done. So, okay, there's a lot of heavy lifting going on and I'll just find one of these operators. But if we can, and we can prove it's self-adjoint, then we're in business. That's the Riemann hypothesis right there.
Give me a function and I don't actually see another attempt.
Huh?
It's not obvious how to show that all the zeros have real part 1/2. So
Yeah.
this feels like it's not trivial.
Yeah, I mean,
the observation is already non-trivial.
I guess so. I mean, a priori, this wasn't actually taken. Nobody wrote this down until the 70s, because until then there is no evidence that something like this should actually be true. A little bit in the 50s, but
Did
but
people always think the Riemann hypothesis is true, or
well, in Riemann's original paper, what he says is, surely all the zeros have real part 1/2. I don't really know how to prove it, and I don't really feel like it right now. So leave it for someone else. That was his conjecture.
Real margins are too small.
Yeah.
Yeah, but he said, yeah, that's probably true, But he said, I have better things to do with my time.
they always say?
He invented, Riemann.
It was his one paper on number theory. He had only 10 pages to do it. So come on, give him a break.
That's true. He only had 10 pages.
His paper was 10 pages long.
Because he ran out of paper. Is that why?
No, he just didn't want to write more.
10
He
pieces of
just
paper.
dropped it and left, I don't know.
That's a cool move.
That's pretty funny. What was he saying? Yeah, Hilbert also said, yeah, it's called Hilbert's conjecture, because at one point he said in seminar, apparently, I think that the solution to the Riemann hypothesis is going to come from Fredholm's work on kernels of self-adjoint operators. And I mean, none of these were said, written down. They were just idle musings by these people, but somehow it got their name attached. So that's what we're going to try to do. We're going to try to search for this magic operator. But before that, we're going to go back just a little bit and talk more about, why we even care about the Riemann hypothesis. So I'm going to talk about why the Riemann hypothesis, maybe I'll do it like this, part one. Zeta and primes. This is the part where I talk about the sort of analytic number theory stuff. And this is the part where, this is going to motivate our construction of this operator later. All on board?
Wait, so are you saying that you proved it? Like you constructed?
I have the startings of a bunk proof. Together we can put it into a truly bunk proof. I need the time.
You didn't come up with this operator.
Well, the thing is, okay. There are a lot of operators that people have suggested, and I'm going to suggest a new one.
Whoa.
Now I haven't checked anything about it, so there's no reason to think it would work. But you know what? I think I'm getting somewhere.
Yeah.
Yeah. I want the
Really
pizza
excited.
party.
This might be a particularly sophisticated bunk for the Riemann hypothesis.
Yeah, that's what I hope for. One that looks indistinguishable from reality. Okay, how does the Riemann zeta function say anything about primes? Okay, so how do we measure primes? So here's how we're going to measure the distribution of primes. We're going to consider the function pi of x, which is going to be the prime counting function. It's going to be the what am I going to write this out? I'm going to call it the number of points in the set. It's awkward notation. I give you a number x, you tell me how many primes are less than or equal to x. So it's like this staircase. It jumps at 2, it jumps at 3, jumps at 5, so on and so forth. Okay, and now just because I'm saying it now, let me give you a different measurement, which is going to be the one that's more convenient for us. This is the prime power counting function. What I'm going to do is I'm going to sum up over all numbers less than or equal to x. I'm going to sum up 1 over n if the number is a prime to the power of n and 0 otherwise. So what I'm doing here is I'm counting all the primes below me, yes, but I'm also counting all the squares of primes. And each of those contribute with 1/2. And then all the cubes of primes, which contribute to 1/3, and so on and so forth. It's just another way to these are not really that different from each other. The statement is that pi of x can be retrieved from capital Pi of x. If you can understand this, then you can understand that, and vice versa. No, not that different. Now let me show you some pictures of these. I'm going to show it to Sam and the people online first. The top one is a graph of big pi, the smaller one is little pi. Big pi is counting more things, so it's always going to be bigger. See their little staircases? Kind of seem what shape do these look like they're making? Kind of loggy, I don't know about you.
Maybe a little greater than that, or
It's a little bit greater than log.
silver log.
Prime number theorem, which says in simplest form that pi of x goes like x over log. Oh my god, it's busted. Now let me give you actually a little bit more of a more refined one off the bat. Or what I can say is the density of primes as a function of x is 1 over log x. And this gives you a more refined estimate, which is that pi of x goes like the logarithmic integral function, which is defined to be the accumulated density up to x. Okay. And this is a better approximation than this other one over here. So that's pretty cool. So what we have here is basically this is a this logarithmic integral function is a smoothed count of the primes. Now, now I want to ask, what happens if we, oh, I'm skipping ahead of myself. Yeah. So what if we cut off this smooth part? Basically, we get rid of this average density distribution and we're just left with the fluctuations of the numbers of primes around this average. So this is what the Riemann function is going to tell us about. It's going to tell us about these fluctuations. So that's just going to keep that in the back of our heads for now.
You have a picture of that.
Of the fluctuations, I do not. Let me draw it. It kind of starts small, it goes up, it goes down. Most of the time it's down, actually. There's a conjecture that it's always down, but it actually crosses infinitely many times, proved by Selberg in or someone else in like the 30s. But we didn't find the first example until actually like the 70s, because the first crossing is at like 10 to the 13 or something like that. Something crazy. So that's an example of like an example in number theory where the first kind of example is happening on really, really big numbers. Seems some more. It's proven that it's processed infinitely many times, but finding them happens really far away.
It's so crazy like that.
Yeah, I don't know. So I mean, there's this statement that number theory is quite like physics because it's an experimental field. The only difference is that analytic number theory has much more precise experiments than real world physics. Okay. Zeta and primes. So here is a fact about the zeta function, which is going to give us all of our relationship with prime numbers, which if you haven't seen before, this is a lovely little guy. It's called the Euler product formula. Instead of summing over natural numbers, we can take the product over primes P of this function. Let's write this as n to the negative s. Just okay. People seen a proof of this before?
In some YouTube
videos. Okay, this is so much fun. Okay, let's just take this right-hand side. 1 over 1 minus p to the negative s by the geometric expansion formula is equal to 1 plus p to the negative s plus p negative 2s plus dot dot dot. Okay, which I'm going to rewrite p to negative s plus p squared negative s plus dot dot dot. So now the product of all of these is going to be equal what? You're going to have 1 plus p to negative s plus dot dot dot. Let's do 2. And then we have the same thing for 3. And then the same thing for 5. Now we expand it out. So every term in our expansion will have one person from each of these coefficients. It'll have one term of each of these sums. So we have the term that looks like 1, and then the term that looks like 2 to the negative s, and then the term that looks like 3 to the negative s, then the term that looks like 2 times 2 to the negative s, then the term that looks like 5 to the negative s, then the term that looks like 2 times 3 to the negative s, and so on and so forth. Basically, what we're doing is we're choosing a prime power for every prime and adding those all together. But those are just the natural numbers in their in their prime factorizations. And that's the proof. Isn't that cute? That's really fun. Lovely little exercise. So, okay, now the zeta function actually looks a little bit like it has something to say about prime numbers, you know? Like, it's a product over primes. But now we're going to use it to actually get the prime counting functions out. And the following is a really lovely bit of Fourier analysis that Riemann was doing. He really goated with the Fourier analysis sauce, if you know what I'm saying. Here's what we're going to do. Where did I write this? Yes. Yeah, let's just do it like this. Okay. What I'm going to do is I'm going to take the log of the zeta function. And I guess you'll see where this all comes together and why I'm doing all this shortly. Okay, log of this infinite product is equal to the sum of the logs. And I'm just going to take the -1, put it out in front. 1 minus p to the negative s. Then I'm going to write this out in terms of its Taylor series expansion. Okay, so each term is now going to be, so we're summing over prime p, and we're summing over integers n, and we're contributing 1 plus, let me make sure I'm not being a fool. Yeah, p to the negative s plus 1/2 p to the negative 2s plus 1/3 p to the negative 3s, and so on and so forth. Okay, so now we've represented the log of this as this crazy sum. And then what we're going to do is we're going to represent.
Wait, where's the n?
I wrote it as an expansion. Let's do 1 over n p to the negative n s. Yeah, so that's just the condensed form of the Taylor series I wrote out before. Okay, what I'm going to do is I'm going to represent p to the s as a Fourier transform. Okay, how am I going to do this? Okay, what I'm going to do is I'm going to consider the integral from some number a to infinity of e to the negative s, x dx. So Fourier, because s is imaginary, this can be either a real s and you get a Laplace transform, or imaginary, you get a Fourier transform, kind of the same thing. Okay, what do we do with this? We can evaluate this integral, and what we get is that we get negative e to the sa over a. So we're going to plug in a is equal to log of p. So we can represent this sum up here as the sum of 1 over n times the integral of p to the negative n, or of n log p to infinity of e to the negative s x dx. Right? Because I take this guy, plug it into here, and then that becomes that guy up there.
N log p.
Yes, let's do it better. Log of p to the n. Okay, I'm just taking this number and representing it as, let's put this a different way, 1 over n times the Fourier transform of the indicator function of the region from log of p to the n to infinity.
Wait, am I being silly? Here we have like
Mhm.
we're dividing by a, but
Sorry, thank you. Yes,
okay.
because this s goes out in front, because you need to,
Yeah,
when you take that
okay,
integral.
yes.
Thank you. So I actually, you're right. I need to multiply it by s over here to get rid of that down there. Okay. So let's write this again. Log of c of s is equal to, let's pull that s all the way out front. We have this double sum of the Fourier transform of, let's just use the linearity of the Fourier transform now. So take the Fourier transform of everything inside, sum 1 over n indicator function from log of p to the n to infinity. Okay. So what does this thing look like? What does this function look like? So let me just say, so I have.
Hey, there you wrote c when you meant zetas.
Thank you. Yeah. There we go. I'm getting better at writing zetas because of this.
They look good.
So we have this sort of log 2, which is that which contributes to this, and then we have a log 3, contributes to this, and then a log 5. And then we have the 1/2 of the log 4. And then log 9. And all of these get added together. And so like we're kind of like accumulating them, right? Each of these guys is go all the way out to that side. And for each number, what does this count? Like the value here, it counts how many of these bars it intersects, multiplied by their weightings. So the things that contribute once are the primes, the things that contribute 1/2 are the prime squares, the things that contribute 1/3 are the prime cubes, so on and so forth. This right here is the Fourier transform of this modified prime power counting function. Right, this one over here, because
This
I'm
is
counting.
some sort of metaphor. Sorry, my bad.
This is a literal statement, right?
Yeah.
Not a metaphor. Like I compute this thing, and it just is the Fourier transform. So that's like really slick, you know?
Yeah, why doesn't everyone just say that? They're like, why do we care about the Riemann hypothesis?
Because it gives you the Fourier transform of the stupid thing. Now let me do you one better. Let me just rearrange this a little bit. Because we have the Fourier inversion formula, which means I can take this guy and move it to the other side. So I have that prime counting function is the Fourier transform of log C of S over S. Maybe it's a minus sign. No. That's pretty busted, you know? So now Riemann was like, can I figure out what that Fourier transform is? Can I solve that integral?
And this is where sorry, keep going.
So, I mean, at this point, it starts to get a little bit complicated because what he has to do, basically, he's like, I don't know about this guy, but like, well, this guy has like poles at the zeros of the zeta function. You'll see, right? Because each of those contributes a 0 to here, and then log of that gives a pole. So he's like, well, what if I just found some function that like was an entire function, didn't have a messed up pole, that had the same zeros as the zeta function, and then worked with that instead. So he introduced the C function,
Oh, no.
which is defined to be the product over all of the 1/2 up front, the product over all of the zeros rho of the zeta function of 1 minus S over rho. Right? What he's doing is he's basically saying, let's just like literally put down a 0 at every single like 0 of the zeta function. And when I say zeros here, I'm not including the trivial zeros, by the way. So let's put a 0 at every 0 of the zeta function. This has the same 0 structure as theta of the zeta function that we want to care about. But this guy, we have a formula relating I guess computing zeta of S and C of S in terms of gamma. So, okay, now what we do is we figure out that like, okay, this was just you just put zeros in those places. Okay, how close is this to the actual zeta function? Their difference is going to be an entire function without any zeros, mostly, and then that's kind of basically given by the gamma function plus some other change.
And how do
I don't know. I mean, it's in Riemann's paper, so like it's just kind of. I don't think Riemann really proved things, but vibe-wise, he's kind of pushing around stuff, you know. So you mess around with the equations, you get this fact here, and then you use this instead for the log guy, and then you are counting the poles of the log. This Fourier transform is equal to the integral of log C of S over this contour that looks like this in the complex plane. This is the contour that you have to use to take the Fourier transform. I didn't write the Fourier transform. The S. Something like that. So this is like the Fourier transform that you need to take, and then you use this formula to get this expression for C of S in terms of things involving the gamma function, and a sum over zeros. And the net result is something called the Riemann explicit formula. And let me write this down. The Riemann explicit formula says that pi of x is equal to the logarithmic integral of x. So that's the smooth part. Yeah, let me just write the whole thing out and then I'll label it.
Is that logarithmic integral of I to the row?
Logarithmic integral of x to the row.
Sorry, that's what
Yes. T squared minus 1 t dt. Okay, what do we have here? We have the prime number theorem. Okay. We have chunk change. And then we have oscillations. The oscillations of the weighted prime counting function relative to the prime number theorem are given explicitly by a sum over zeros of the Riemann zeta function. This is the content of, this is the main result of Riemann's paper. And the first proof of prime number theorem.
Well, don't we need to get some sort of bound on the zeros to get that?
I think because the zeros are all inside the critical strip, that's enough. Because you know how large the real parts are, you know that this part can't grow too fast. So you don't need to know that they explicitly equal 1/2 to show that this guy doesn't overwhelm.
I thought we needed to show they didn't lie on the boundary of the critical strip.
Oh yeah, maybe. You know, they need to show that they can't be 1. I think that follows from the functional equation. So, like, that's good. Okay. This guy. Yeah, that's what Riemann did. Now, okay. This is pretty awesome. I'm going to, so what this means is that basically we can write down, like, we can take a sum of only a finite number of zeros at the zeta function, and then this whole guy over here gives a series of approximates of the full prime counting function. So let me show you a picture that I stole from Wikipedia. I'm showing it on the screen, and then I'm going to show it to people and describe it a little bit. So this first one here is a picture of just the modified, the weighted prime counting function relative to the logarithmic integral. Okay, nice and smooth, matches it up nicely. Here it is for Sam. Then what we're going to do is we're going to include 4 zeros, and you can see that this blue line is now a little bit more wiggly, kind of conforming to the bumps of this function. Okay, now let's try like 80 zeros, and you see that it's basically doing a Fourier expansion, right? The zeros of the zeta function are acting as terms in the Fourier expansion of the oscillations of the prime counting function relative to their smooth baseline. That's why we care about the zeros. They literally give you Fourier coefficients. So I want to rewrite this in one other sense, which will make this more clear. And I'm going to do this on a board that I'm going to save especially for this formula, because this is the formula that we're going to generalize or to build off of. Let's hope I have enough room for this. So I'm going to suggestively call this for the trace movement. Okay. And what we're going to do is we're going to give a different equivalent form of Riemann's explicit formula that has to do with, that was due to Weil. So it's called Weil explicit formula. And here it is. So I'm going to let B be a test function on R. Okay, what I'm going to do right now is I'm going to describe basically a function that relates the distribution. If you take all of the zeros, lie them on the critical strip, put a Dirac delta on each one, that gives a distribution. You can do the same thing for the prime numbers. Take the prime numbers, lay them out, put a Dirac delta on each, that gives you a distribution. I'm going to give you a formula relating these distributions. Now I can't just so in order to relate these distributions to one another, I need to probe them using a test function, and that's what this guy's going to be. It's just some nice, smooth function, has everything you want to have of a function, compact support, all of that good stuff. Zeros be rho n equals 1/2 plus I Rn. Rn are imaginary numbers, potentially.
This is assuming. Oh,
No, I'm about to.
Oh, sure.
Yeah, so with so if all these Rn's are real, then the Riemann hypothesis is true. Okay, so what I'm going to do is I have the sum of this function tested against the zeros of the zeta function. So this is a sum over zeros. Then I'm going to take this and I'm going to take this distribution and I'm going to subtract off a term that corresponds to the smooth part, basically this Li over here, to the smooth part of the zero counting function. Now this is a kind of an annoying little formula. I'm going to write it down so it feels like I'm not lying to you, but the actual form of this formula does not matter. Let's talk. Okay, so that's the smooth part that we subtracted off. So it is, you should think about this guy right here as being like the smooth distribution of the count of the zeros of the zeta function. It plays the same role as this Li up here. I don't really know how to get from one to the other, but they're equivalent.
Wait, so these rho n, these are the zeros of the zeta function?
These rho n's are the zeros of zeta. Yes. Now this is going, so this left-hand side has everything to do with this rho function, but the right-hand side is going to have to do with, it's going to be a sum over primes p of log of p times the sum over n of now the Fourier transform of this test function. Okay. What do I have here? I have sum over zeros. I have a smooth part. I have some chunk change. And on the other side, I have a sum over primes distributed over these primes here, these n log p primes. And then I have a constant term. Okay, that's what I have going on. And how should I interpret this? Roughly what this says is that the distribution of zeros is Fourier dual to the sum of a bunch of Dirac deltas at the logs of prime powers. With a coefficient given by log p over e n log So this is just a much more literal thing of what I was saying here. I was saying these kind of look like a Fourier transform guy. Here I'm saying something much more literal. Literally, if you take the zeros of the Riemann zeta function, get rid of the smooth out part, so it's just the oscillation of the density of the zeros around the baseline, then the Fourier transform of that as distributions is equal to something concentrated on the logs of prime powers. This is now what is the content of the Riemann zeta function? The content of the Riemann zeta function is that like these guys are all real. And if these guys are real, then I have literally a statement about Fourier transform saying that this distribution on the real line is dual, it's Fourier dual to this other distribution. That's the Riemann hypothesis. So, okay, how are we feeling? Like that guy? Yeah, okay, so let me just talk a little bit about this and we'll take a break before we do other stuff. I could lab for an hour already. Okay, so what are some implications of the Riemann hypothesis? One is that it implies that the logs of these prime powers, these guys here, are a discrete distribution, a point-like distribution whose Fourier transform is also point-like. We have a name for these. We call these quasi-crystals. So I'm going to show this to Sam first. So this is a picture of the Fourier transform of the Penrose tiling. If you take a Fourier transform of a regular tiling, something that is...
When you say of a tiling, you mean of the indicator function of the boundary?
Sure, or just any drawing of the symmetry of the Penrose. So let's say the boundary. Okay. So just the grid of lines.
Sure.
If you started with a regular tiling, then the Fourier transform would be supported on a grid. It would be point-like. Now the Fourier transform of the Penrose line, I didn't actually show you. You see right here, it's supported not on a grid, but on something with a little fancier symmetry, on this fractal-like shape. But it's entirely point-like. There's no continuous. It's a quasi-crystal. It has symmetries, but not like all the symmetries. I don't know. So basically, the content of the Fourier transform is that the primes are themselves a quasi-crystal. So one potential approach to solving the Riemann hypothesis is classifying these 1D quasi-crystals. So it's suggested by Freeman-Dyson. Another implication, sort of the best pop math interpretation of the Riemann hypothesis. If the Riemann hypothesis is true, then the Fourier transform of this prime signal has a completely discrete spectrum. And that spectrum is given by the zeros of the Riemann zeta function. What that means is it's entirely decomposable into sine waves, or the primes have music in them. You can play them. You can play those Fourier transforms on top of each other and hear what it sounds like. And I'm going to do just that. So this was created by Michael Berry, who is going to be doing some of the other stuff that I'm going to talk about later today. The more recent paper where he tried to figure out what the music of the primes sounded like. So first I'm going to play the Fourier decomposition of the zeros of the zeta function, which is basically playing notes corresponding to these primes. And let's take a listen. Now you're including one prime at a time as you go along. So you get this note that's just upwards. Higher there. Oh, that's you too. We don't want that. There's another one. I don't know what this one is. Maybe this is the much higher reading. So that's it.
Determined by ratio of
it's spacings between the frequencies. And those could be anything. This is, I think, a fact about additive number theories. There's very little additive structure to the primes. This is a thing we want to prove. Like all good things in math, the Riemann hypothesis is a very hard problem because it is about trying to intertwine additive and multiplicative structure. We're doing a Fourier transform of the distribution of primes. We're looking at the additive regularity structure of something which was derived from the multiplicative structure of numbers. A large number of very hard problems can be phrased like this.
Like the ABC.
Sure, but I mean, even the questions like, what can the determinant of a matrix whose entries are all positive look like? Completely open problem in linear algebra. Basically nothing about this, as far as I know. And it's basically because on one side you have the determinant, multiplicative. On the other side you have the coefficients of the matrix, additive. And those two do not like to talk to each other. It's like if you were doing Lie groups and Lie algebras at the same time, but you didn't have the exponential map to pass between them. It's nasty, Okay, and here's another one. Here's what the primes sound like, where you're adding in the coefficients associated to the zeros of the zeta function instead. So this is kind of the dual signal to the other one. And you'll hear that it has a different... I don't really know what philosophical point to take from this, but I think it's really cool that look at that scale going on. What they're adding in points for each step they add in points here. And it's planning. And then it's music into primes. Didn't say it was good music.
Beautiful.
Actually.
One last thing. I don't want to say this because I'm blabbing too much. Okay, break time.
Okay, that was bad.
Okay, I finished talking about my just pure number theory stuff. Now I'm
No,
gonna
this
go
is
to
good. I've
standard.
been trying, like, I periodically like opened articles about this throughout my math career, being like, do I know enough math to like easily understand why this is true without actually having to sit down for like 4 hours and like read through a complex analysis textbook?
Mhm.
And the answer apparently is now I do.
No, that's good.
That formula up there at the top left,
Bonkers.
fucking insane.
Isn't it also like so nice, you know?
Yeah.
You write it as a Fourier transform.
Well, because like this sort of trace formula nonsense is crazy. The like, the what is it called? The functional equation.
Mhm.
Also fucking
I mean,
crazy.
I think that one's the easiest to prove because you really just mess around with the integrals, but it doesn't look like anything.
This tells me
Yeah.
why I should care about this. That tells me why I should care about this.
And it's nobody like puts this in a box, you know? I don't understand why. It's so good.
Bonkers.
You know why they don't put that in the box? Because usually when people write this, they don't take logs of the primes. Oh, I did this wrong.
Those equations wrong.
Yeah. Oh, I'm plugging in logs of primes to everything. So this should be ln of x. Whatever. Because usually people don't do it with ln of x, which means this Fourier transform becomes a Mellin transform, which is just take the Fourier transform and then do a u sub for x goes to e to the x.
Logs make sense because you're trying to turn multiplicative structure into additive.
Yeah, but I mean, in the context of the Mellin transform, if you write, oh, this thing is the Mellin transform, this other thing, I'm like, I don't know what the Mellin transform is, you know? So, yeah. How's it going, Sam? Are you good?
Great.
Any questions? I don't know.
Not yet.
You do number theory? Is this a thing you've seen?
I never really did too much analytic number theory. I don't know. I'm these days I'm more into like zeta functions and like graphs and stuff.
Oh, yeah.
That'll be my question at the end.
Huh?
At the end, my question is going to be about is there a version of this for like graphs
There are
or
zeta.
for
Yeah.
because there's zeta functions for graphs or hyperbolic surfaces.
I will.
There's
I'm
a zeta
talking
function.
about hyperbolic surfaces next.
Okay, graphs are the same hyperbolic surfaces.
They're the same? That's
Yeah.
easy. Okay.
Because there's like Laplacian. Yeah.
Did you like spend time doing geometric theory or something?
What did you say?
Did you used to do like geometric group theory or something like that?
Not really. I took Donnie Weiss's class
Oh, okay.
one time.
Yeah. Well, just saying like graphs are the same as hyperbolic surfaces is like a very like that considerably narrows the fields of math that you must have experience with in order to say that phrase.
I guess so. I got that from number theory. Like there's also an area, there's like it's probably less common, but there's also an area of number theory where that's like what everyone thinks.
Presumably the parts that you use technically.
Sorry, what did you the part that use what theory?
Theory.
Well, I can't hear. The distance is like too far, I think, from the
The
speaker.
parts of number theory that use Teichmuller theory.
Oh, I have no idea about Teichmuller theory. No, like certain like p-adic stuff.
Yeah, I mean,
Because like graphs are kind of like p-adic curves. I don't know, in a very loose sense.
that's interesting. Okay. Because like all of the sort of hyperbolic geometry, if you look at it from like a group theory standpoint, basically transfers over to graphs, here considered as like now Cayley graphs of fundamental group of hyperbolic things. So like the type
Yeah, that's interesting.
the moduli
Yeah, I
space.
never really.
Uh,
Yeah,
like
I don't know if I've ever learned about this from that perspective.
yeah, that's interesting.
It's cool.
Come on.
Yeah.
Ready, spaghetti? I don't know how long I've been keep blabbing. I made like 12 pages of notes. I don't know.
What page are we on?
5, 6, big 6, like halfway through. Yeah, that's fine. People can leave whenever they want. I thought this is like, good cultural context, I feel like this is good as a society, right? Okay.
As long as it can.
There we go. All right, now we are going to do part 2, which is going to be zeta functions and dynamics. So the fundamental theme of this is the following analogy between number theory on one side and dynamics on the other. Okay? And what we're going to do is we're going to say that like dynamical systems, so just to frame what I mean by this, in my context, I'm going to mean I have a manifold, I have a vector field on that manifold. And we're interested in seeing how points move around according to that vector field. Now, we should think about the primes in number theory analogously to how we should think about simple closed orbits. Now, there's many orbits that one can make in a dynamical system. For example, if I have one that goes around all the way back to where it starts, then I can make another orbit by just going around one more time, and so on and so on. We call the orbits where it only goes around once simple orbits, and these simple closed orbits are going to be analogous to prime numbers. Sometimes people call these prime orbits. People call them that. I heard people say that. Like a prime geodesic. I don't know.
I think I've heard that like
Okay. Very good. Very good.
It's related to the analogy with multiple.
Wow.
Simple closed loop.
Yeah. That's not a thing I know about. So I guess what Yuji's referencing is
closed whose
primes are.
whose closed orbits is precisely the set of knots.
You can.
Yeah, that's crazy. That's awesome. But what Yuji's referencing is that like there's an analogy where primes correspond to free manifolds, and the the knot complements corresponds to like prime free manifolds, and decomposable ones are like prime numbers, something like that.
Well, also prime knots are prime numbers.
Yeah. Not what I'm saying. Okay, what's the point? Then integers, which we should think about as like products of primes, correspond to what? They correspond to, I guess, collections of simple orbits, which in the language of ECH we call these orbit sets, which are just multi-sets of orbits. Okay. So using this analogy, we can define what's called. So let's for a free manifold Y with a vector field R. I'm going to just introduce some notation here. So I have my set. I define P to be the set of simple closed orbits. And I'm going to have, for gamma, a simple closed orbit. I'm going to say P sub gamma is the period. How long do you have to wait for my point to go all the way back to where it started under the flow of this vector field? Then I'm going to define what's called a dynamical zeta function. And I'm going to define it completely analogously to my Euler product, which I just erased. Which is I'm going to take a product over prime orbits. And I'm going to take 1 over 1 minus. And what am I going to put here? Before I put primes to the negative s, in this case, I'm going to take the exponentials of the periods. So e to the negative s times the period of gamma. Okay. And this is going to be sort of my analogy to the Riemann zeta function. Now, I can write this. This is for our ECH heads over here. Like just how I can expand the Euler product to get a sum over integers, I can expand this to get a sum over orbit sets. So I have a sum over orbit sets. And then for each orbit set, I get a contribution from the action exponentiated. So the total period of all things in my orbit set. Okay, ECH people, does that make you happy? I don't know. Yeah, that's the thing that we saw in class. Like we see this guy in class. So we can kind of think about this dynamical zeta function as a Fourier transform of the actions of all of the orbit sets, if we wish.
The action is just here.
Action is the sum of the periods of all the guys inside.
Oh, sure.
I'm just using that notion because that's what we do in.
No, I got it.
Okay, now what do we do? Okay. Now, why was I bringing this up? So this is where we're going with this. Is basically we're going to be building. We're going to be building. We're going to be building dynamical systems whose zeta functions look like the Riemann zeta function, and we're going to try to analyze the zeros of these guys. So to do this, we're going to use one more line in this analogy, which I did not give myself enough room to do, so I'm just going to put it at the top, which is that if instead I no, wait, if instead we did number theory analogized with with a Riemannian manifold, then we can get something a little bit more precise. Now, every Riemannian manifold is a natural dynamical system associated to it. You take a ball, stand at a point, throw the ball in a direction, see what it does. It's the geodesic flow. So we have the simple closed orbits now are prime geodesics, or simple geodesics. And now we have something that's analogous to the zeros of the Riemann zeta function, which we will see in some of these following examples, why this is considered the right thing in the analogy. These zeros correspond to eigenvalues of the Laplacian. What does that mean? You can think about the Laplacian, if you'd like, as a quantum dynamical system. You give it a function, and that function evolves according to the wave equation on your manifold. The periodic orbits, quote unquote, are given by eigenfunctions of the Laplacian, and their periods are given by the eigenvalues. So this is sort of a classical, like, if you wish, I'll talk more about this analogy later, but this is classical, and this is quantum.
And it's not literally true that the Laplacian eigenvalues count. Simply doesn't. It's just morally.
You'll see.
Oh.
You'll see.
It's the crazy one. My bad.
So what am I going to do with this? I'm going to give examples of when we can make these sort of counts. So what is this saying? Like if I look at my trace formula here, on one side we have, or my explicit formula, on one side we have a distribution, something that measures the zeros of the zeta function, and on the other side we have the primes. So in this world, we're looking for something where on one side we have the sum of a test function measured against the eigenvalues of some Laplacian, and on the other side we have the Fourier transform measured against the lengths of a geodesic. And this is what I mean by link. So if we find like the reason why I'm suggesting that this analogy exists is because I'm going to exhibit a number of formula that look kind of like this in sort of increasing complexity. And then we will notice that these formula look a whole lot like this one up here. Okay, happy with where we're going? All right, so our first example. It's going to be classical fact from Riemannian geometry from Fourier analysis that I never remembered until this. Here's how it goes. So we're going to consider the manifold M is equal to the manifold S1 with a metric G. No, there's not very metrics Riemannian metrics you can put on S1. The only invariant is the total length of it. So with length 1. So on the prime side, on the sort of right-hand side over here, there's only one prime geodesic. With length 1. Which is the thing that goes around the circle. Okay. The eigenvalues, so the Laplacian, if I use my coordinates theta of the circle, the Laplacian looks like negative the second derivative. Okay. So the eigenfunctions are e to the 2 pi I k x, k theta, sorry, or k inside of z. And the eigenvalues are k inside of z. K squared. Yeah. Oh, okay. So then what we can do is we can write the following formula, which is this fact right here, which is that the sum, if I take any nice test function, I add it up at every single integer value, then that's equal to what you would get is if you add up the Fourier transform over every integer value. This is called the Poisson summation formula. And like I can rewrite this in a form that makes it look a little bit more like that over there. What I can write is the sum over n of the eigenvalue over k, I guess, of the square root of k squared. So this is the eigenvalue, lambda k eigenvalue in there. If I put in these eigenvalues, square roots of them, into this test function, and that's equal to the sum over all orbits of the geodesic flow of the Fourier transform applied to the length of that orbit gamma. Because remember, this is equal to a sum over n, how many times the geodesic goes around itself, of the length of that, which is itself equal to n. Maybe I should just... So what are we saying here? We're saying left-hand side, we have spectral side. Right-hand side, we have lengths of orbits. These are the prime numbers on one side, and the other side, we have the things that look like the zeros of the zeta function. And we're saying that these are Fourier dual. When we probe them with test functions, on one side we take the test function, on the other side we take the Fourier transform. The distribution of eigenvalues is Fourier dual, the distribution of lengths of closed orbits. The content of the Poisson summation formula. Okay. How do we feel about this? I mean, I kind of did a lot of like taking a simple thing and dividing tea leaves out of it, I guess. But are we happy with what I'm saying? Let me give you a more convincing example. Okay, a more convincing example comes from the Selberg trace formula. Now this one's a little bit more complicated. So we're going to let sigma be a surface endowed with a hyperbolic metric of constant negative curvature. Okay. And then we have two sides. We have, I already denoted that, and I have the eigenvalues. So what we can do is with this surface, we can consider the Laplacian, and we can consider the eigenfunctions and eigenvalues of the Laplacian. Look at the spectral theory of this surface. Zero. So the eigenvalues are all greater than 1/4 for a hyperbolic surface. With lambda 1. Okay, so we have the ordered eigenvalues of our surface. Closed hyperbolic surface. Okay, and what we are going to do is write down the trace formula. I'm going to do this back over here because this is our coalition of trace formulas. So we have the Selberg trace formula. And what does it say? I'm going to copy down a big long equation. Most of this, the details don't matter. You can kind of cross your eyes. I'll point out the things that do. So on one side, we have the sum of the test function applied to the square root of the eigenvalue minus 1/4. So remember, all of that, that's always going to be a positive number because 1/4 is the spectral gap. Every eigenvalue is greater than 1/4. Let's bring Sam over. Then what are we going to do? We're going to subtract off.
This is at the bottom
Mhm.
there. Lambda squared is bigger than like 1/16.
Shoot.
Maybe one.
I want 1/4 there. I think the spectral gap is 1/4 over here. So, but let's just put 0 over here and then it'll be okay.
Why square?
I'll tell you why this is a reasonable thing to do later.
They didn't square the eigenvalues.
There I didn't square the eigenvalues, that's true.
Oh, okay.
So this I'm taking the eigenvalue, I'm like just like over here, how in order to make this work, I took the eigenvalue and I took its square root.
Yeah.
That's kind of what I'm doing here too. Like I have to modify the eigenvalues a little bit before I plug them in. So, I mean, maybe one thing yeah, okay.
Is this going to be related to like singular values and adjoint operators or symmetrical operators?
I mean, yes. So there are many ways in which you can mean that sentence, and I think all of them are, the answer is yes, but in some of them I know why, and other with them I don't.
Okay.
So maybe I'll keep talking and you can ask again.
Yeah.
Okay, so I have my distribution of eigenvalues, and then just like before, I'm going to subtract off a smooth part. So we're going to have the area of this hyperbolic surface, which is the total Riemannian area, divided by 2 pi. And then we're going to integrate against basically the smoothed distribution. So we're going to integrate against tanh. Now, I never looked this up. I was meaning to. What does tanh look like? It looks like like this, right?
No, that's arctan. This is
Shoot.
the hyperbolic tangent.
I need to look this up. I was gonna.
An exponent and then fills over some other exponent.
Yeah, but it might tanh of x. Yeah, okay, yeah, we're perfect. It does look like this.
Oh,
From tangent to +1 and -1. So what I'm saying, this basically says that the smooth part of the density that I'm subtracting off after you take the square root looks like tanh. And what does that mean? That means that the density looks like tanh. So like maybe we can try to integrate the density to find a number of eigenvalues less than a given number. So the integral of tanh looks like this. It's asymptotically linear. Oh, no, maybe I want this. Yeah, I want that. Oh, that's what I did wrong. Okay, there it is. We're safe. So the distribution of square roots of eigenvalues is linear, meaning the eigenvalues are distributed square rootly.
Quadratic.
Shoot. Anyways, this is supposed to reproduce the Wild law.
I was
Which
about to say.
this is
okay.
supposed to. I didn't work this out beforehand because I didn't even look at what tangent was. But this is supposed to be like the Weil law right here. So the Weil law gives the asymptotics of like how many eigenvalues we expect there to be at each given density
So what
just
you're
by
saying
the
is
area of the
Michael's
surface.
Varela invariant conjecture is going to apply the Riemann hypothesis.
Huh, yeah, we're doing that. That's where we're going with this. So this is the smoothed part. And what is this equal? It's equal to the sum over geodesics over prime geodesics. And what am I going to take the sum of? I'm going to take the sum of law of the length of the geodesic. Maybe let's use a lowercase p just to be consistent with my notes. And then I'm going to sum over all of the different multiplicities that I can have in that geodesic. And what I'm going to sum is the Fourier transform of my distribution times the associated length of that multiply covered geodesic divided by this cinch formula. NLP over 2 minus e to the negative NLP over 2. And this is the Selberg trace formula. Okay. Now, what I want to do right now is stress. Okay. Distribution of eigenvalues. I smooth it. What does it equal? The oscillations around the smooth distribution are governed by a sum over geodesics. They're governed by a distribution, and that distribution is concentrated at the lengths of the geodesics. Coefficients don't matter for now. That's what they're saying. What we have is a Fourier duality between the eigenvalues of our Laplacian and the lengths of the closed geodesics. Notice that this looks really similar to the explicit formula for the zeros of the Riemann zeta function. So let me just write this out to be explicit.
When was this done, bro?
56. Or this was like the 30s or something when it was in. It was yeah. So what do we have? We have the Selberg trace formula. Looks a lot like the explicit formula. And we can do one better. We can introduce the Selberg zeta function, which is roughly the dynamical zeta function of this system. That's not a zeta. So I'm going to define the zeta function of sigma pi to s to be, it's not just going to be the formula I wrote there. I don't know why. But here's the formula. It's the product over prime geodesics, then the product over integers n, and you're going to take 1 minus e to the negative s plus n LB. So the normal dynamical zeta function, you'd simply take the product over primes of 1 over 1 minus this guy. Here, you're not inverting and you have this extra infinite product. I don't know what that means, but this is a zeta function that we can build out of the dynamics of our hyperbolic surface. And then Theorem is that rho is a 0 of the Selberg zeta function if and only if rho times 1 minus rho is equal to an eigenvalue of the Laplacian. Now, what does this mean? Maybe I'll write it here. around in space. Really jamming things in. Your own. So, rho times 1 minus rho is real. And what this tells you is that rho is equal to 1/2 plus I. If I write rho equals 1/2 plus IR, then I have that lambda n is equal to 1/4 plus R squared. Rearranging, or R is equal to the square root of lambda minus 1/4. So because each lambda is greater than 1/4, because that's the spectral gap, R is real. So the Riemann hypothesis holds for zeta of sigma.
Does it just generally true that every time you write down a zeta function, it should have a critical strip?
Yes, this is because that's not actually a property of zeta functions. I think it's a property of Mellin transforms, you know? Like you can just check where does your thing converge, and you know it's going to converge above 1, you know it's going to converge below 0. You probably have some functional equation that flips you around s equals 1/2. So every zeta like function has a critical strip. So what is this saying? I mean, basically what we've done is we've said the proof is that the zeros of the zeta of sigma are exactly the eigenvalues of some 1/2 plus the square root I to the square root of delta minus 1/4, and this is a self-adjoint operator. So the proof that the Selberg zeta function satisfies the Riemann hypothesis follows the outline of Hilbert-Ploya. We found an operator that linearizes the Selberg zeta function. It's the Laplacian. That's basically encoded inside of this trace formula. And then we use that to get a Riemann hypothesis. So this is evidence that, like, you know, maybe there's actually something to this parabolic conjecture. You know, maybe we can actually linearize this because the Selberg zeta functions behave a whole lot like the Riemann zeta function. But try as we might, you know, after 100 years of people trying different hyperbolic surfaces, nobody's found one that whose Selberg zeta function agrees with the Riemann zeta.
So we're supposed to imagine this sigma as being some version of this.
Sigma. Which sigma?
Sigma being the hyperbolic.
Sigma is my hyperbolic surface. Basically, every sigma gives me a different Riemann zeta type function. All of those satisfy the Riemann hypothesis.
Okay.
None of them are your actual Riemann zeta
So
function.
your attempts are literally maybe there's sigma for which
Yeah.
the zeta is the number 30 zeta.
Yeah.
Okay.
And we couldn't find one.
Uh-huh.
That wasn't my attempt. That was, but this was why Selberg was looking at these zeta functions, because he thought he could use these to do the Riemann zeta function.
Yeah.
But
Wait, sorry,
yeah.
Elliot.
Mhm.
Is this actually known in this case?
Yes.
Like, is this like Selberg's 1/4 conjecture or something? That like lambda.
There's 1/4 conjectures, but we know the spectral gap.
Is it known that lambda is always greater than or equal to? Like, isn't this Selberg's 1/4 conjecture that lambda is always greater than or equal to a quarter?
I don't know, but I think we know that for other reasons. Because I've been to talks where people have said that. But I am not an
Okay.
The Laplace operator on Moss waveforms of congruent subgroups are at least 1/4.
Yeah, so that's this right now. I've just did it for compact surfaces where this is known. Now, if I want to do number theory stuff, it's important to consider cuspidal surfaces or other weirder types of surfaces. In which case, I don't know what the state of the art is.
And in general, I guess, congruent subgroups.
So congruent subgroups, basically, I determine a surface by choosing a subgroup of SL2Z and modding out by those symmetries.
And congruence ones are specifically in.
Okay. What am I saying? Yeah, I mean, that's pretty crazy, you know? I mean, but it really makes us think, like, what if we could come up with some system that wasn't hyperbolic surfaces, that did have this trace formula, and that you could actually get, you know, the Riemann zeta function as the dynamical zeta function. You know? Wouldn't that just be peachy? I would think that would be super cool. So what I'm going to do is I'm going to move on to a new board, and I'm going to talk about.
Just one more question.
Yes.
Like the sort of primes you get here, are they kind of distributed with a similar sort of density to?
Yeah. I didn't write down the percentage thing, but theorem.
That's how to compare the.
The number of, I'm going to define a function like this, which is going to count the number of the set of prime orbits of any orbit, I guess, such that the length of that geodesic is less than equal to t. So it's maybe like a similar thing to the prime countable function. And then I can use this trace formula and use my knowledge of this while law here to give me what the lengths look like, how long they are, and how many there are of each length. And the answer is, oh, it's dropped you. And the answer is that this goes like, t over log t. Exactly what you'd expect. So they do actually have the same asymptotic distributions. I think, I don't know why there's a log t. Doesn't make sense. Maybe it does. There's a log t because I actually want this to be e to the t, right? Because I'm taking an extra log when I'm comparing these two. So I need this to be e to the t. Yeah. But yes, it's the same formula.
Is this, that's not very impressive funny stuff.
No, I don't think so.
No, she proved that's that.
I don't, it is.
She did the count for simple closed geodesics.
And the length spectrum of them. How they grow.
Yeah.
Huh.
Yeah.
I thought we just knew this from the trace formula.
This might not be simple closed geodesics.
Yeah, this is all geodesics.
Yeah.
Which is different.
Yeah, right.
One more quick question.
Mhm.
In fact, like the function field setting with number 34.
Mhm.
Analog with the Riemann hypothesis is that it's not too hard to prove.
Mhm.
Do you know if there exists a proof of this sort of problem?
Yeah, so in the function field setting, which it looks like the wild conjecture, right now I'm just regurgitating what I hear people say without understanding it. But there is a proof in the function field setting, just basically contained in the wild conjectures, and it does proceed by linearization. Namely, they find a certain operator, the Frobenius operator, and they show that the eigenvalues of the Frobenius operator basically give the zeros of the associated zeta function. Basically, we should think about the Frobenius operator as a discrete dynamical system, and then take the dynamical zeta function of that, and then that agrees with the zeta function for function fields, something like that. Anyways, they linearize the problem. They're all good, except that the way the proof works, it doesn't prove that this operator is self-adjoint. There's no natural Hilbert space structure that we have on our vector space that we can just use to say, oh, it's self-adjoint, therefore it's real. Instead, it argues by some sort of deformation in families type argument. Now, this is why Peter Sarnak says, like, he thinks this Hilbert-Ploya conjecture is naive, because all the proofs we have of Riemann hypothesis, except the Zelberg zeta function, which is sort of designed to work like this, apply through deformation of families rather than through finding a Hilbert space structure and showing it self-adjoint. So, maybe someone understood that. I didn't.
Deformation of families as in you deform.
I don't know. If you start with a thing you understand, you deform it, you show that the zeros don't jump off of the real line, off of the critical strip as you deform. Some argument like that.
Contact.
It's given contact, sure, why not? You know, let's go for it. Oh, what time is it? Okay, whatever. I'm still talking. You're welcome to. I guess one good thing about doing this in the summer is I don't have to. I don't know, maybe we should keep things shorter or something. I don't know. Okay, I'm going to describe for you an extremely general way of creating self-adjoint operators. And this is really the whole point. This is the whole reason why I gave this talk, is because I want to understand the theorem that I'm about to show you. What we're going to talk about now are semi-classical trace formulas. Okay, and the approach we're going to use is that of quantization. This is what's going to give us our self-adjoint operators that we're going to try to use to get zeta functions. Okay, so quantization. You know, everybody has like the thing that they write in every talk. You know, just like every talk you give, you have to define what thought foliation is. I don't know. This is my thing. So I always draw the following diagram. Quantization is a scheme, a name, like there's many types of ways to do this, but in its essence, it's a scheme that takes a symplectic manifold and turns it into a Hilbert space with a nice inner product structure. And it takes a Hamiltonian function, that's just some smooth function from the manifold to R, and it turns it into a self-adjoint operator. So let's call this Hilbert space curly H. H hat makes H to H. Okay. Now there's many ways to do this scheme. I'm going to describe one which I don't know if anyone's actually set up in this way. I think it must be buried somewhere in these like crazy you can probably extract it from previous results. I don't know, but I'm going to explain it in this way because it looks the most similar to like contact geometry type setups. Because I know we like that stuff. Okay, so here are what we're going to use. We're going to let W be a Weinstein domain. Now, for people who aren't symplectic in the room, let's have a little box for Weinstein. This is basically the same as pseudo-convex, if that helps. I don't think it does. But what this means is that my manifold looks something like this. Like there's a part where it's like weird stuff happens, and then there's a part where it goes off to infinity. So I'm going to call this the weird stuff, and I'm going to call this part this W bar. And the Weinstein structure in particular means that there's a vector field on this guy, even, which expands things out. So we have this vector field, which is called the Louisville vector field, which has the property where the flow of the vector field for time t, if you pull back the symplectic form, which is our measurement of everything, then you get the exponential scaling of that symplectic form back. So this is a thing that just zooms in your manifold. Now, the Weinstein assumption is that V is equal to the gradient of U for some U. I mean, it's weaker than this, but this is the one I'm going to use. Okay. So I have some function on my manifold, which is big down here. What does it look like? Which is big down here and small up here, and its gradient flows you outwards. Maybe it's small down here, big up here. Its gradient flows you outwards and expands out the manifold. That's our Weinstein structure. Okay. Now, in particular, we're going to take a symplectic completion. Which is W bar, which equals W union the boundary of W times R, or I guess times an interval. Interval. So I'm taking the boundary of W, which was this part here, and then I'm just kind of stretching it out, and I'm continuing using this Louisville vector field, so that it looks kind of like it has a product structure. Okay, so that's the setup that we're going to be considering. Now I'm going to choose the Hamiltonian H to be linear. Let's call this extra coordinate, this like distance coordinate, let's call this S, I guess. In S outside of a compact set. So what does that mean? We're looking at functions which this is the same setup that we use in symplectic homology. So our function, it does some weird stuff inside of the W section in the compact region, but as once it gets to the completion part, it just goes straight up, straight linearly. Okay. Happy with that? Okay. Now what am I going to do with this? Let's go to a new board. Now I'm going to use this function to define an operator. And the way I'm going to do this is using the canonical complex structure on this. So I will note that by a wonderful theorem of Ellie Ashberg and Cesar Back, I guess, that W has a canonical, I think it's canonical complex structure. What that means is we can actually talk about W as a complex manifold and as a Riemannian manifold and as everything. It's a good time. So what we're going to be interested in is these linear Hamiltonians. Maybe I'll say
Is it literally a complex structure or like a normal?
literally a complex structure. It's crazy. You can always find a way to take an almost complex structure and make it integral. Let me just write one more thing over here. XH agrees. And let's write Y is the boundary of W. So this Hamiltonian vector field is something which is a vector field I get from my Hamiltonian. It's going to start swirling me around the level sets of the Hamiltonian. Now at each level, right, it's going to be like, it looks linear in this coordinate, which means it's something that's going to be swirling around my boundary of W part. Now this, in this setting, I set this up so that XH agrees with the Rade field on Y, I guess. So what have I said here? What I've said is that basically I'm considering this Hamiltonian because its dynamic agrees with the canonical dynamics on the boundary of your Weinstein domain, which is those of the Rade dynamics. So our quantization and any sort of dynamical statements we get from it, because of this setup, should actually have something to say about the Rade dynamics of this contact boundary. Which is why I spent all this time trying to get this set up. Okay, are we happy? Questions? What I've not yet defined is a Hilbert space. So find a Hilbert space.
What type of quantization is this?
I'm about to describe it. I haven't done any
Or
quantization.
like is this what people mean when they say geometric quantization?
I'm doing Berezin-Toeplitz quantization. I'll put that up this corner. I mean, it's kind of like a Toeplitz quantization of a geometric quantization, like they kind of go hand in hand. Okay, I'm going to define H to be the following Hilbert space, which I'm going to denote by HL2 of W with this weight U. What is this going to be? It's going to be the intersection of the ring of holomorphic functions on W bar, okay, which is the symplectic completion, intersected with L2 functions on W bar with weight U, which is the set of functions, or I guess the Hilbert space completions of the set of functions such that the L2 norm, defined as the integral over W bar of norm of f squared, the pointwise norm, times this exponential of this weight function. Is finite. Okay, this is kind of a handful, but example.
So if you like that action.
Huh?
If you like the action of physics.
Not the action. I mean, I'm thinking of this as a no, not the action yet. We'll see that coming up later. This weight function is sort of like a Gaussian. That's how you should think about it. A Gaussian on this weird space. For example, if W is equal to C, then my Louisville function mu is equal to Z squared. Maybe I want e to the negative mu. And my HL2 is going to be holomorphic functions on C that are L2 with respect to the Gaussian norm. Okay. And this is a very nice Hilbert space because this is actually isometric to L2 of R. This is called the Siegel-Berg transform. I mean, I guess I'm not really going to explain this, but whenever I'm talking about this stuff, this is really what I'm thinking about in the back of my head. Like you can do this all very explicitly, even just in a complex number, and you still get pretty interesting things. Are you concerned? Are you happy?
No, wait, I'm okay.
Okay. Like this you can ignore if you don't want to know what this means. Like just take this to mean I have defined a Hilbert space. Because the actual structure won't matter. I just wanted to set up a quantization so I didn't feel like I lied to you all, you know? And I'm still lying to you because nobody sets up this quantization and proves the trace formula. So I'm just going to say what the answer is going to be. And then, I don't know. Okay, what am I saying? Okay, define MH, okay, as a multiplication function. It's going to be sending me from L2 functions with this weighting to itself, where MH applied to a function f is going to be h times f. And h is a real value function, it scales it up. So what we want to do to define our quantization is to just take a holomorphic function and then pointwise multiply it by h. Okay? So that doesn't work because we're not going to get something holomorphic back because h is not a holomorphic thing. So what we do is we define pi as the orthogonal projection of L2 of this space to the holomorphic L2 of this space. And then we can define quantization of my Hamiltonian as multiplication by h followed by projection back down onto my Hilbert space. So this would take in my Hilbert space and send it to itself. We've actually done something.
Pi on both.
I put a pi on both sides, just like this first pi just doesn't do anything if you start an h.
It sort of sanitizes it.
It's like, yeah, you're sanitizing the input, making sure you're not going to do anything too nasty to begin with. Yeah.
It's just like a little, what, like,
Why this guy?
yeah.
I mean, if it makes you feel better, like, I mean, I put this guy because then I can plug in things that aren't in H, and it still works like I want. I can cover them up if you'd like.
Okay.
Like, if I plug in something in H, it doesn't change. So
Wait, if you plug in something that's not an H, does it actually? Oh, surely
We should put
it
down
does
H.
something crazy different depending on whether you put pi in it. Probably.
I mean, H, yeah, H
Because we're mixing up multiplicative and additive structure.
half the papers you see don't include this second pi.
Yeah.
I don't know. I mean, okay, what have we done here? What does this function do? This function is the closest thing to multiplying by my Hamiltonian, which remember is something that grows really fast. So let me just kind of draw you a picture of this. So let's draw my guy upside down this time. Shade it in a little bit just because I want to flex on you all. Okay, so here's my W, here's my W bar. My function is something which starts small up here and then gets big out here. Okay, so if I plug in a holomorphic function whose density, what I'm drawing right here, is like the region where the function is large, that is the norm squared of the function times this weight function is large. Then what this function does is it takes this guy and it multiplies it by like what level it's at. That makes it bigger and it projects it back down to holomorphic. So roughly, like things which are farther get larger. So if I have something, a function which is like way down here, then my operator will act very largely on it. It'll make it very big. Okay. So what I should think about is that like eigenvalues, let's call them E1 through En with eigenfunctions, which are holomorphic functions psi1 through psi n. Psi I is quote unquote concentrated because it's like has that energy around psi I, it's concentrated around the level set H inverse of EI, right? Because that's the level set where it scales things up by EI. This function is going to live around there. Now, there are some results that make it precise analytic sense in which I can say that this eigenfunction is concentrated. I'm not going to talk about those. I don't even know them. But like, this is why this Toeplitz, this is sort of the intuition behind this Toeplitz operator. It splits up your functions into ones that are in your compact part and the ones that are farther away. Okay. Happy? Happy.
The dynamics of it in the limit does that.
Yeah, so if you, or I guess the eigenfunctions, yeah, sure.
Yeah, eigenfunctions of
If I take the evolution of this operator, then it like rotates the phase of the part from way down here a lot faster than the part up here. Maybe that's a way of thinking about it. Okay, and now we have the main course about why I actually talked about all of this, which is that intuitively, we get eigenfunctions of phase e to the wait, I want to say this. Imagine I had a periodic orbit. Then my quantum state, which has the energy like around here, what I can do is I can build a quantum state, which is kind of like a little snake, snaking around this orbit. You know, it's a wave that's concentrated around the orbit, and we want this wave to constructively interfere with itself. So the total like when it wraps all the way back around, we want the total phase accumulated by this like snake eating its own tail. We want the total phase accumulated to be like proportional to the period. Or I guess the period is the total phase accumulated, and we need that to be about 1, right? So what this is saying is basically like you can design quantum states which live around periodic orbits. And you can use these to build eigenfunctions. And the content of that is that we have an expansion of what the eigenfunctions look like, or the eigenvalues look like, in terms of the lengths of these periodic orbits. So what I'm going to do is I'm going to fix E, a regular level of H inside this like part where the dynamics look like the rate flow, just to make things nice for me. P is the collection of simple closed wave orbits. Okay. And for gamma inside of P, right? Gamma n for the n-fold orbit. And now we're going to go all the way back to this point and add our last trace formula. See if I have room, because this is kind of a nasty one. Okay. So what I'm going to do is this trace formula is going to be semi-classical. It's going to be an asymptotic. And the formula is that I'm going to sum over contributions around of the energies around the fixed energy, one that I specified, divided by h bar. And what is this going to equal? I'm going to have So what does this do? Zooms in.
So wait, H bar is
It's some asymptotic parameter I'm introducing.
Okay.
So as h bar goes to 0, this zooms into E. So we're looking at the dynamics near the energy level E. And what does it say? H bar to 1 minus n. So we have one term, which is the sort of constant term that measures the volume of the level set. And then we have a term which sums over prime orbits. It takes the action, which is the period, because in a Ray orbit, the action is equal to the period. Takes the action of that orbit over 2 pi. Then it takes the sum over ETI and to the phase accumulated around that orbit times a phase factor given by the Conjecture index of that orbit divided by this crazy thing where this Pn is the first return map on the contact structure. Like the linearization of the first return map. We're taking,
I said you betcha.
you betcha. And then all of this is applied to the Fourier transform of the action of this n-fold orbit. Plus lower order terms. Okay. Full formula. What's the point? The energies concentrated around level set E are controlled by the volume of that level set plus a sum over periodic orbits of something that lives entirely in the actions of the orbits. And you see how these are Fourier transformed relative to one another. You know, like just like all of those above, the spectral theory on one side, the length spectrum, the dynamics on the other side are related to one another. And this is the semi-classical trace formula. Okay, let's take a look back and sort of like bask at this and look at it relative to the other two. First off, Hilbert trace formula, special place of the semi-classical trace formula when applied to the geodesic flow on the negatively curved surface. This hinge thing here measures the volume of the level set, I think. This denominator here is a measurement of the first return map. It's exponentially large because what this is saying is that we have hyperbolic dynamics. The first return map stretches things out in one direction, squeezes things in the other. Geodesic flow on a hyperbolic surface is hyperbolic dynamics. That's why we get this sort of cinch here. We have the Fourier transform term. And we have a phase term that's like the Conjecture index, that's somewhere in there. We have this action here and an action there. So that's sort of the explanation of like what's going on behind the terms in the Hilbert trace formula. Secondly, this thing looks a whole lot like that thing. So the question is, can we design a Hamiltonian such that this integrand right here agrees with this integrand up here? And then such that this sort of asymptotic term about the densities of the eigenstates agrees with that density of the eigenstates. Like, if we can prove that, and we can prove that these lower order terms go away, see if I can Hilbert trace formula is exact. There's no lower order terms. Magic little thing about hyperbolic surfaces. Prove the lower order terms go away, then we have constructed what they call the Riemann dynamics, the hypothetical classical dynamics that underlie that once you quantize them gives you an operator who, according to the explicit formula, the zeros of that operator should be zeros of the zeta function. Okay, so a lot of things because it's getting late. So let's take a pause here and recollect ourselves.
Next, you're gonna tell us what.
I don't know. Next, I might stop if it's being blabbing for 2 hours.
Wait, can I ask one?
Yes,
Did we
please
talk
do.
about self-adjointness of this operator?
Yeah, so that's the magic thing.
Mhm.
If we construct an operator in this way, this guy is automatically self-adjoint. It's really easy to check. We just take the complex conjugate of this, and all it does is complex conjugate this guy. And if he's a real function, then he's self-adjoint. So somehow the goal of the proof is no longer to show self-adjointness. That comes for free.
You just
All
have
we
to-
have to do is construct an operator who's, who has the right dynamics and whose zeros give you the right
all
thing.
we have to do.
All we have to do. So here is how we get a bulk proof of the Riemann hypothesis. We come up with something that does the correct semi-classical dynamics. It has the correct orbit structures and stuff so that its trace formula reproduces the exact formula for the zeros. We hand wave away this ... and then we say we're done.
And then we get a million.
I feel like if we
dollars.
manage to do that, you might even be able to just not hand wave away the ... and then be done. And like actually prove it. Like that's you're like, okay, we can come up with a bulk proof by doing the hard part,
No,
then
it's...
waving away the easy part, then we're done.
So
And then
okay,
we pizza party.
and then have a pizza party. Yeah. So things I can do right now. I can explain to you where all of these terms come from. Basically, this is a formal application of the stationary phase approximation to an integral over loop space, which is pretty awesome. Or I can try to tell you what this tells us about the hypothetical Riemann dynamics and give some guesses about things that could solve the Riemann hypothesis.
Can I get a summary about the hypothetical Riemann dynamics just so I can like go and ponder what's it
You want me
gonna
to-
look like?
Yeah, I mean, the goal of this was to fantasize. Do you want me to write them down?
Yeah, I want a bullet point list of it.
Yeah. No,
Conjectures.
Yeah, okay, let's do one.
Well, just like if I can check off all those boxes. I'm
Where do I want to go?
Riemann.
Yeah, let's do it right here. Okay, Riemann dynamics. Let's actually put it under here. I don't need the trace formula anymore.
You're not gonna erase the trace. Okay, fair.
That's the whole point. I don't need my quantization stuff. Like, I spent so long trying to think about which quantization scheme I should tell you about, because every scheme has its own trace formulas, but for some reason not the Toeplitz operators, which really annoyed me.
I'm very curious about this bio law thing
Mhm.
and like how is it possible that there's some sort of general principle that bio laws should be enhanced to trace formulas?
Yeah, that's the subleading asymptotic for a while law. Hypothetically,
Okay, but then you say Conley-Zender index, and I hear Ruel invariant.
I do too. That's the thing. That's the stupid thing, is that this has every single ingredient of floor homology. It's all in here, but nobody knows how to relate this to floor homology data. I have not.
That's
I
because floor homology is stupid.
No, it's because this is here's the difference. One is floor homology. Like, you know how floor homology is the homology of this action functional?
Yeah.
This guy is the exponential integral of the action functional. It contains less data. But like somehow there should be a way to get these guys to talk to each other. And I don't know how, and that's what my project is. Is like, can I get quantum mechanics to talk at all? Like the spectrum of these guys should have a lot to say. Like, these should be symplectic invariants. They should be. They should obstruct embeddings. They ought to. But I don't know how to do it.
Yeah.
Okay, what am I talking about? Yeah. Okay. So the Riemann dynamics. So let's read things off from our list. The first thing, I have a whole little guide over here. Okay, first thing, compare this term to this term. So one is that the that the periods of simple orbits is equal to the set of log of p for p prime.
Which is like automatically nearly
Yeah, and if we find this, then this is equivalent to saying the zeta function of our contact manifold is actually equal by the Euler product formula to the Riemann zeta function. So, I mean, already finding this, just any system where this is true would make me happy. Like, this is probably where most of the hard stuff happens.
Oh, I was gonna say this rules out almost all rate flows in expression.
Well, this is what I wanted to talk to you all about, is basically how much can we rule out? Like, can we actually find any, like maybe there are no contact manifolds that are the Riemann dynamics. Maybe we can just straight up rule that out. Okay, number 2. Here's another very damning piece of evidence. Is that this Conley-Zender index phase has to contribute has to contribute this minus sign. Which gives me a fact which I think is already basically unreconcilable, which is that for every non perhaps simple orbit, the Conley-Zender index of gamma is equal to 4 plus 8 in Z. 4 plus.
I wish that I wasn't an idiot who didn't know anything about Conley-Zender indexes, but that
It doesn't make sense because when you go twice around, the Conley-Zender index measures the rotation number of the symplectic guys, you know?
Yeah.
So when I go twice around the orbit, you expect it to double. Doesn't quite, because you have to do some floors and stuff, but on average it doubles. Which means you expect that if the primitive one has 4, then the next one should have 8, then the next 16. You expect that these numbers should alternate. That the contributions from these would alternate positive, negative, positive, negative, positive, negative. And I don't think they do. So that's weird. But apparently there is a way around this if you work on dynamics over adelic function fields or something that phones the geometry, which really scares me. I don't know. Number 3.
like for me it's 3-dimensional wave dynamics or bust, unfortunately.
Yeah. Okay, number 3. I can read off this bad boy as this bad boy. That tells me what the first return maps are. Which tells me that of I minus P gained to the N is equal to E to the N, or just P to the N. So in particular, you see, or maybe I'll write this, E to the N of P. So we see that the rate of expansion of the first return maps is directly proportional, or it's directly proportional to the length of your total accumulated orbit. So you pick up a uniform amount of expansion every time you go around any orbit. What this implies is that we have uniformly hyperbolic dynamics.
On periodic orbits.
On periodic orbits. Which we expect to be dense because the system is chaotic, which I'll see next. (3A), which is not part of up there. This is dynamic, which we know because the pairwise correlation of zeros so that's like I take any 2 zeros, I compare them against each other. Look at what that looks like, the distribution of that. It is identical in the limits. This has been proven, this has been statistically verified, all sorts of things.
Proven and statistically verified.
Well, this has been proven and stronger things have been statistically verified.
Okay.
It's identical to a random Hermitian matrix. Take a Hermitian matrix relative to the Gaussian norm of H star. Trace of this. This gives you a norm on the space. This gives you a measure on the space of Hermitian matrices. The grand Gaussian ensemble, whatever. Like you can look at a random matrix from this, and the eigenvalues of a random matrix like to repel from each other more than you'd expect. And the amount that they repel is identical to the amount the zeros of the zeta function like to repel. Which we expect from chaotic systems. I don't know if this is a proof or if this is just what the physicists do, but like that's what we know about that. Okay, moving on to the next. So, okay, what are we looking at so far? We're looking at a thing whose orbits are all the logs of primes, who like who is uniformly hyperbolic and chaotic, and we know the Conjecture indexes, and one more thing. This guy, or this does not look anything like this guy up here. But what they both control is the smooth part of the number of zeros. So we know the while law, which, as I said before, was that the number of eigenvalues of a Hamiltonian operator less than or equal to e, maybe I didn't say this before, number of lambda n such that lambda n is less than or equal to e, this counting function for the eigenvalues has the asymptotic growth rate of the volume, symplectic volume of the sub-level set of your Hamiltonian. So the number of eigenvalues less than the given value is the smoothed version is the volume. That's kind of this volume right here. And we know that the number of zeros less than a given value e goes like e over log e. And then plus like 7/8 or something like that. Let's write it correctly. E over 2 pi times quantity e over log e over 2 pi plus 1 plus 7/8 plus 1. That's basically hiding inside of number 4 up there. So we have the full asymptotics for the number of zeros, and then the question is we need the sub-level sets to have this area. One more thing, 5. Trace formula must be exact. So after we found our dynamics and everything like that, we have to find a way to quantize it. And we have to prove that the semi-classical asymptotics of the number of eigenvalues does the right thing that we want. And we have to prove that by the trace formula, the oscillations do the right thing we want. And we have to prove that the trace formula is exact, which is a very like situation specific thing. You know, the prototype for this is the Selberg trace formula. It's exact. But okay. That's the Riemann dynamics. So that's what we need. There's a lot of things that we know about this system, what it would have to do. Yes.
I think this is the wrong trace formula.
Okay.
Okay, because like all of these are very, or like at least like 2, 3, and 4 are very consistent, like with each other,
Mhm.
And highly contradict one.
Is that true?
So
You want exponential growth rate of your.
you need
orbits.
exponential growth rate of your orbits.
Uh-huh.
Because you're never gonna have anything sufficiently. I mean, it is possible that there exists a rate flow with zero topological entropy
Mhm.
that has entirely hyperbolic orbits.
Yeah.
Um,
Oh, you need zero topological entropy to get this growth rate of simple. This is simple orbits, keep in mind. Not all orbits. But still, yeah.
I wonder,
Yeah, we can.
I don't. If we can figure out a way to rectify that, this feels like you just want to find like a rate pseudo and also flow that does what you want it.
I feel like the log p is inevitable because that's the only part where it actually relates to number theory. Like we have examples of functions that do this, and 3 and 4 and 2, and they do everything except for 1.
But like if you replace it with xp, you know.
I mean this is
Yeah.
this is the trace formula.
Yeah, because no one likes taking exponents of terms. They all take log of terms.
I don't know if we can pick and choose in this one, you know. I feel
Well,
like
but like just generally philosophically, if you take the logarithm of a number,
Mhm.
that is the sum of the logarithms of its prime components.
Yeah.
Like summing up logarithms of primes is a very natural thing
Yeah,
to do.
yeah.
Exponents of primes is a very goofy thing to do. You
Yeah.
should be taking exponents of numbers, logarithms.
Yeah,
of
that's
primes.
yeah, mixing additive and multiplicative.
Yeah.
Okay, I will say one more thing, and then I can stop ranting for 4 hours about this stuff. I'm sorry, I'm torturing you all. My guess.
This one's zero.
Yeah, this is I'm putting all my money on this one.
Yeah.
Consider the geodesic flow on a surface with Lorentzian metric. So what does this look like? I mean, I kind of skipped the part, but like what it looks like is on each fiber, the Hamiltonian looks like x squared minus p, looks like xp, I guess, on each fiber. It's a quadratic form, but it's not positive definite. It has signature on it. Like this is the Hamiltonian that generates this. The Hamiltonian is you basically plug in the tangent vector into your Lorentzian thing, but there's a different signature. Anyway, the point is this guy, the level sets look like this. And if you cut them off in the right way, then the area under this region is equal to E over 2 pi times the log of E over 2 pi plus 1 plus 7/8. It is exactly the right, like if you find the way to quantize this correctly, what they found, what Berry and Keating found, this was a paper that everybody loves to cite back from the 90s. This is basically the entire premise of the talk, is that this Hamiltonian x times p has exactly the right smoothed number of eigenvalues. Of course, the oscillations are totally wrong because it has nothing to do with primes, but it has the hyperbolic dynamics. It has this part too. It has that part. It has everything except the part that's actually number theory. Now, what you could just do is take this XB Hamiltonian and put one copy of it on every point on a surface. That's what this Lorentzian dynamics thing does. And now we can get interesting dynamics, but still have the same Weil law. So we can have the right first order approximation to the number of zeros of the zeta function, but we have a chance of actually getting those oscillations to match up. So now the goal is simply reduced to a very simple goal, which is to find such a metric whose geodesics are element. And then we prove doing Riemann hypothesis. Thank you all for coming.
Which you can't do because you're trying hyperbolic dynamic.
I can't do, well, I mean, this is not even really I don't know how this is a weird little contact manifold. I don't know, it might be uniformly hyperbolic, I don't know anything about this, but basically, I know, but it's Lorentzian. I don't know about the Lorentzian dynamics, those could be hyperbolic.
T3 does not admit an analysis.
It's not T3, that's not the structure. Because the level sets are non-compact. It's a non-compact free manifold. It's not T3.
Oh.
It's a messed up guy. Okay, that's the thing. That's what saves us. It's complicated enough that I don't know it doesn't work yet. So it must be the answer. Right? So and what's good is I also know how to quantize this, which is the quantization is the Laplacian relative to this metric. Of course, this is a hyperbolic operator, not an elliptic operator, so everything catches and burns and explodes and a plane crashes into the second tower. And it's not very good, but if we find a way to quantize it, then we're good. This is my bunk proof, right? You write down one of these, then you wave your hands about Laplacians, and then you send it, put it on Vixtra,
Wow.
Okay, thank you all for coming. 2.5 hours.
Okay, actually, here's my take. There's no way the Riemann hypothesis comes from torus dynamics.